In this section, we're going to just focus on finding our center of mass, or where everything balances. Super important in construction. You always want to make sure you support your center of mass so stuff does not fall down. We'll look at the most basic of ideas here in this above diagram. Let's say that you could think of this as a seesaw, and you want to figure out where you're going to put your balance, or what we call our pivot. So if we look at this triangle here, this would be our pivot. Where do we put our pivot so everything's balanced? Well, in this diagram we have this larger mass to the left that we call m sub 1, and we have this smaller mass to the right called m sub 2. So it makes sense for us to put our pivot closer to the larger mass so that everything's balanced. So if you imagine our d sub 1 as being some distance from the pivot, d sub 2 being a distance from the pivot to the second mass, then, and here it doesn't really matter the order, I'm going to just call this x sub 1 like a point on that bar. So if I take the x sub 1 and I subtract we'll call the pivot x bar. So that's the notation that we're going to use for our center of mass, or a pivot. I can describe these distances as the subtraction between them, and then do an x bar minus, and I'll call this x sub 2, the point at where it's resting on that bar. Okay. So if I were to look at the distance away from the pivot along with the mass of these objects, then what must be true is that these guys have to be equal. So if you just multiply the mass times the distance, it's got to equal to mass times distance. If we take this equation and we set it equal to 0, we get this next equation. And now if I were to distribute m sub 1, m sub 2, combine like terms, and then solve for x bar, my pivot, I would get this last equation for x bar, which would be this m sub 1 x sub 1 plus m sub 2 x sub 2 over m sub 1 plus m sub 2. So if you look at the numerator here, this m sub 1, I think I'm going to use the thing, m sub 1 x sub 1, m sub 2 x sub 2, that's what we call our moments about the origin, but I'll just say moments. And then when you look at the denominator, all we're doing here is we're just adding up the mass. And that's just with two objects, or a two-mass system. But we can extend this idea to any n amount of objects. So imagine, wanted to highlight that. So imagine n amount of these masses, and then we multiply each one by their distance away from the pivot, and then add them all up. Then you get this summation from 1 to n, where we have mass times distance. That has to equal 0 in order for everything to be balanced. And then we have this equation for the x bar, where you have the total moments over the total mass, which again we can write it as a summation. So these are separate masses that we're adding up. Now imagine if I were to, instead of having a summation, I would write this as n goes to infinity. Well, as n goes to infinity, what that gives us is it gives us an integral. Remember, an integral is just a sum, right? But it's a special sum. So everything's sort of smashed together. And it would be an integral where you're integrating moments, total moments, over total mass. So we'll talk about that in just a second. Let's look at example 1. We want to find the point at which the system is balanced. So I have an m sub 1, x sub 1, m sub 2, x sub 2, m sub 3, x sub 3. simply, where it's balanced, our x bar or our pivot is going to be the m sub 1 times x sub 1, or 3 times the negative 2, and then we're adding it to the sub 2's, 7 times negative 0.5, plus add it to the sub 3's, which would be 6 times 4. And then you divide everything by the sum of the mass, which would be 3 plus 7 plus 6. So that gives me 14.5 over 16, which I don't like decimals and fractions, so if I put that in my calculator, I get 0.90625. And that's it. But again, we're more concerned with objects that are kind of all smashed together, which brings us to our next page, where we're finding the center of mass in a one-dimensional object. So if you look at this diagram, it's just one piece, but notice there's shading to it. It's a little bit misleading because this is a one-dimensional object. We're only concerned with length. So you imagine this as being a thin rod or wire. And this diagram would actually be, imagine this being a really thin rod or wire. The only reason why we're showing thickness is so that we can show shading. Notice that this goes from light to dark. So what that implies is that towards the left you have a smaller density, and where it's darker you have a larger density. You can kind of think of it as weight, a lighter and a heavier side. So when I would place my pivot, I would place my pivot more towards the heavy side, so things are balanced. So in one dimension, we're only concerned with length. We only have one variable, so our density is going to vary just with the variable x. So since it's one dimension, we're going to integrate with respect to the density function, and it's going to be a single integral. Which brings us to the definition of center of mass in one dimension. Okay? So again, we're just going to have one integral. So to find that center of mass, which is this x bar, it's going to be the total moments over the total mass. So we're going to use capital M to stand for the total moments. And we're going to use the lowercase m to stand for mass, total mass. So we're simply integrating, and I'll look at the mass first because that's easier to understand. So remember that when we find mass, we're integrating with respect to a density function. So it makes sense with one dimension that we have a single integral where we're integrating over the density function. In this case, our density function is that rho function. Well, to find the total moments, which would be this capital M, remember in that summation there was an x times m plus x times m and so on. So it makes sense that you're going to take an x times the density function. We'll go ahead and do an example. Let's look at example 2. Suppose you have a thin 3-meter bar and it's made of an alloy whose density is in kilograms per meter, and that density function is 1 plus 2x. So we're only going to look at this bar from 0 to 3 because it's a 3-meter bar, and we want to find the center of mass. Well, before I even find the center of mass, remember it's a balancing point, where this balancing point is closer to the heavier side. My density function is 1 plus 2x. Okay? Well, when you look at my x values, they vary from 0 to 3. So it makes sense as the x's get larger, my density function 1 plus 2x will also get larger. So when x is 0, the density function is 1. When x is 3, the value of the density is 7. So if I was to put a balancing point, I would think it would be closer to the 3 and further away from the 0. And I want that picture in my head so that when I finally do my computations, whatever answer I get makes sense. I'm going to go ahead and compute the total moments first, which would be the integral from 0 to 3. And remember, we're putting in x times the density function, which is 1 plus 2x, integrating with respect to x. Distribute your x, and then go ahead and integrate. My integral is going to simply be x squared over 2 plus 2x to the third over 3, evaluated from 0 to 3. And when I evaluate that, I get 9 over 2 plus 18. And that would be, what, 45 over 2? Or you could write it as a decimal. Now the mass is simply the integral of the density function 1 plus 2x, which would be x plus 2x squared over 2, which would be x squared evaluated from 0 to 3, and that would give me 3 plus 9, or 12. When I figure out my x bar, my center of mass, it's going to be the 45 over 2 divided by 12. So my center of mass is 15 over 8, which you could write as a decimal as well. Does that make sense? 15 over 8 is close to 2. So that would be closer to the value of 3 and further away from the 0. So yes, this answer makes sense to me. We're just going to do one example where we have center of mass in one dimension. It gets more complicated, of course, when you're in 2 and 3 dimension because you're dealing with double and triple integrals. Center of mass 1 dimension, single integral. Center of mass 2 dimensions, that's going to be a double integral. If we look at this diagram, we want to make sure that the region in 2-dimensional space, so think of it like a flat plate, we want to find where it's balanced. So since it's a point where it's balanced, it's going to need an x and a y value. So you're going to have an x bar and a y bar. Now the x bar is computed by total moment over total mass with respect to x. So this m sub y, this moment with respect to y, doesn't seem correct. But really, the reason why that y is there, and it's a little bit misleading, m sub x would probably have been better, is because we're looking at this x bar as being some distance from the y-axis, which is why it's an m sub y. But it's still going to be total moments over mass. And then you see the y-bar is looking at some distance from the x-axis, which is the moment with respect to x over the mass. Okay. And here our density function rho, because our region is an area, is going to be mass per area. When we talk about these 2-dimensional regions, we just have to make sure that they're what we call closed and bounded. So they're these nice regions that are like in one piece. So it's an enclosed 2-dimensional region. Look, there's no breaks or holes in it. And then we're guaranteed to be able to find a center of mass. We're guaranteed to be able to find a balancing point. Imagine if there were holes in there. What if the balancing point just happened to be where there was a hole? Then we wouldn't be able to balance this object. If the density is constant, then the center of mass is called a centroid. So if you see a problem where it asks you to find a centroid, you can assume the density is a constant density, meaning that you can put any constant real number in your integrand, any number you wish. So typically we usually just use 1, Because remember, when you find the center of mass, you're looking at total moments over total mass. So if the density function is constant, whatever number you put in for the density function will cancel out in the fraction. The definition for center of mass in 2 dimensions, sorry, can't speak today. Can't speak because I have a little kitten on my lap. It's going to be a double integral over the region. Again, your x bar is total moment over total mass, which would be 1 over the mass. And then you compute the double integral, but remember you're putting an x in it if you're finding x bar. You're putting a y in your integral if you're finding a y bar. And they both have density function rho. Again, centroid just means that it's constant density. Example 3, we want to find the centroid, which is good, because if I'm finding a centroid, I can use any number for my constant density. The region bounded by the line, sorry, got a little typo there. The line x is equal to 4 and the curves y equal to the square root of x and y equal to negative square root of x. Well, first of all, this is the 2-dimensional object, which in this case, it's very easy for me to sketch. So I'm going to go ahead and sketch the object. Let's say that this is 4, and I have this line at x is equal to 4. I have the curve y equal to the square root of x, and y is equal to the negative square root of x. All right, and then we have x is equal to 4. What I'm looking at when I want to compute the balancing of this region is this area between these curves. Now, since it's constant density, and you don't have to use symmetry, but oftentimes with these math computations, they can be very long and tedious. So in this case, think about folding this object on the, oops, I always do that, I don't change it to a thin pen. So think about folding this object along the x-axis. The 2 y functions will match up perfectly. So there's symmetry with respect to the point y. Think about where I would put my pivot. It does matter where the x goes, right? But the y value, because of symmetry, and here I also have constant density, the y value for the center of mass, or the y bar, will always be 0. Because if I put the pivot anywhere on the x-axis, which is where the y value is 0, then I've got a perfectly balanced distance with respect to the y value. So if you see symmetry, and again, just make sure that you're real clear about the density function and the object itself. If you do see symmetry, feel free to use it, but you don't have to. You can always just power out the y bar. So I know that my y bar is going to be 0. I just have to figure out what my x bar is. So the first thing I'm going to do is I'm going to compute the mass and not the moment, because to me mass is easier. When I compute the mass, well, first of all, if I look at my y values, the lower curve is the negative square root of x, and the upper curve is the positive square root of x. Remember, I'm doing a double integral now. I have to make sure that I end up with constant limits of integration. And then my x value goes from 0 to 4. When I compute the mass, it's going to be a double integral. I'm going to end with my x value, so that's going to be the outer integral from 0 to 4. The integral on the inside will go from the negative square root of x to the positive square root of x. And since it's constant density, I'm just going to use 1 for my density function. Again, I could use any number I want. And this is dy dx. So computing that mass, it's going to be the integral from 0 to 4 of y evaluated from these square roots, which is simply the square root of x minus the negative square root of x. That would be 2 square root of x. And then that would be the integral of 2x to the 1/2. And that's going to be 2x to the 3/2 over 3/2, which turns into 4x to the 3/2 over 2, or 3, sorry. Evaluated from 0 to 4. So this is going to be 4 times 4 to the 3/2 over 2. Or 3. I don't know why I keep saying 2. If I plug that into a calculator, I get 32 over 3. So that's just my mass, which is usually the easier one to compute. I now need to find total moments, same integral as far as limits of integrations go, which is nice. So it's all going to be the same. The only thing I have to do now is add the x in to my integrand. So all of this is going to be the same, except for now I'm integrating with respect to y first, so this becomes x times y. Square root of x's dx. This would be 2x square root of x, I believe. Which is 2x times x to the 1/2. This is going to be 2x to the 3/2. Which in turn would be 2x to the 5/2 over 5/2. That'll turn into 4x to the 5/2 over 5. Alright, I'm just going to plug this in a calculator. The 0 cancels out and I get 128 over 5. So remember, this is my x bar. My x bar is equal to the total moments, which was 128 over 5, over total mass, which in this case was 32 over 3. I'm just going to leave it as a decimal, I'm too lazy. And that's 2.4. That actually makes sense, because I knew that when I found my center of mass, since as I go from 0 to 4 on the x-axis, notice that this object gets larger, so it makes sense that the point of balance should be closer to 4 and further away from 0. So 2.4 seems like a reasonable centroid. And then finally that would be a point, right? So I have to write it as the ordered pair. So this was, the last example was when we had a constant density. So now in example 4, we're finding the center of mass of this rectangular plate. And you're given the rectangular plate, the dimensions of it. But notice that it has a density function that's not constant. So in this case, my density function, rho, is 3 minus x. However, I could still use symmetry. Again, if you're not sure if you can use symmetry or not, don't use it. Just compute your x bar, y bar, power out those integrals if you wish. notice that my density function doesn't have a y in it. It only has x, which means the density function will vary with respect to x, but not with respect to y. So if I sketch out this region and it turns out that I geometrically have symmetry with respect to y, I could just figure out the balancing point with respect to y. So it's always like a halfway point when you think of where it balances. Well, let me sketch the region. The region has negative to positive x values, but the y values go from 0 to 1. So I'll kind of sketch it down here. So x is going to go from, I'll just make this a negative 2 and a positive 2. Y goes from 0 to 1, and it's definitely not to scale, but it does something like this. And I have my plate. So as the interesting density function, notice it's 3 minus x. So when x is negative 2, the density function is positive 5. But as the x's get larger, the density actually gets smaller. So it looks like if I were to balance with respect to x, it would actually go closer to the negative side, because it's got to be on the side with the higher density. But my y values will always balance at the halfway point of the y values. So since the y values go from 0 to 1, by symmetry, I can say that my y bar would have to be 1/2, right? It's the halfway point between 0 and 1. So here I'm just using symmetry again, which you don't have to use. I'm going to need to compute my mass, so I'll do that first. It's going to be a double integral. Since my region is rectangular, that means that my x and my y values are constant, and notice that they're given to me already, so I don't have to figure those out. So I'll put my x values on the outside and my y values on the inside. I have the density function 3 minus x, and this is a dy dx. Integrating first with respect to y gives me 3y minus xy, evaluated from 0 to 1. Okay, so when y is 0, it's gone, so that's going to be 3 minus x. And then evaluating with respect to x, oops, sorry, don't want that integral. This becomes 3x minus x squared over 2. So I get 6 minus 2 minus negative 6 minus 2, which gives me 12 for my mass. Now let's do the total moments. Same limits of integration. I just have to remember to add an x into my density function of 3 minus x and dy dx. So again, it's a lot of repetition here. We have 3x minus x squared. Which gives us 3xy minus y squared. I think I'm just going to write this as y times 3x minus x squared. Integrating with respect to y, it's 1 times that minus 0 times that, so it's just going to be 3x minus x squared. And then antiderivative here, 3x squared over 2. minus x to the third over 3. I get 6 minus 8 thirds minus 6 plus 8 thirds. Double check me on this. So this would be a negative 16 over 3. That makes sense because remember I'm trying to find my x bar, which is going to be this negative 16 over 3. So a negative number divided by a positive 12, it's going to give me a negative number, which I expected. I knew my center of mass would have a negative x value. So negative 4 over 9 makes sense to me, which means my center of mass is an x value of negative 4 over 9, and the y value is 1/2. So remember, it is a point, so you do need an ordered pair at the end. So now we're moving on to finding the center of mass for a three-dimensional object. So imagine this three-dimensional object that we're balancing. So it's going to balance on an ordered triplet, a point that has an x bar, y bar, and a z bar. And when we find our x bar, we're finding total moments over mass, where the total moments are with respect to a distance away from the yz plane. So it's a m sub yz. The y bar would be the moment with respect to a distance from the xz plane. The z bar would be a moment with respect to the distance from an xy plane. So similar to the 2-dimension, we're just adding another dimension, which also means we're adding another integral. So here, center of mass in 3 dimensions means it's a triple integral. However, the process is still the same. You have the x bar, you have your moment over mass. When you do your triple integral, you have your density function, you add in the x. Y bar, density function, add in the y. Z bar, density function, add in the z. So in example 5, we want to find the center of mass of the solid cone with a constant density, which is good. We have a constant density. Oh, I did it again. I got that thick bar. So constant density, we can use an integrand of 1, or the density function. We could use 1. It's going to be bounded by the surface z equal to 1 minus the square root of x squared plus y squared, and z equal to 0. So it's a cone. Let me just do a quick sketch. So we have this cone, and when x and y are 0, we're at 1. But then it comes down to the plane z equal to 0. So it's a cone facing downward, where its vertex is at a z value of 1, and then it comes down to the xy plane and stops there. Now, when you look at just the xy plane, remember we're setting up this triple integral. Where it's going to hit on the x and the y axis is, remember what we're doing, if z is equal to 0 and y is equal to 0, then x has to be 1. So that would be the x-intercept. And same with the y value, it would have to be 1. So when we look at in the xy plane, look at this object, it's just the unit circle. It makes sense to me to get rid of the square root because I have an x squared plus y squared. So it makes sense to me to change that to r's and thetas. And maybe I'll use cylindrical. So I'll have a dz r dr d theta. So my z is 1 minus the square root of r squared just becomes 1 minus r. Now the base, that unit circle, that implies that my theta values are going to go from 0 to 2 pi. I'm going to go all the way around. And since it's a radius of 1, my r values are going to go from 0 to 1. So I have a theta, I have an r, and I have a z value, which makes sense to use cylindrical coordinates. Do I have symmetry? Well, my density function is constant, which is good news. And when I look at this cone, you can imagine it rotating about the z-axis, which means that I have symmetry with respect to the x-bar and the y-bar. They're going to be 0. Again, if you don't get why we could use symmetry, then just compute the x-bar and the y-bar. So the only thing I really have to do is compute the z-bar. Now, I could compute the mass by looking at the triple integral, but remember my density function that I'm using is 1. So a triple integral with an integrand of 1 is just computing the volume. So in this particular case, my mass is actually going to be the volume of this object, which is simply a cone. So I don't have to use a triple integral to figure out what my mass is. However, if you didn't see that, that's fine. The volume of the cone is going to be 1/3, you could do the triple integral. It's going to be 1/3 pi r squared, and in this case r is 1, times the height, which in this case is 1. So my mass is simply going to be pi over 3, and I didn't have to compute that triple integral. I didn't have to compute the triple integral to find x bar and y bar. I just have to compute the triple integral to find z bar. So I have my lowercase m, my mass. I just need my total moments with respect to the xy plane. It's going to be a triple integral. My limits of integration are all constant except for my z values. My z values are going from 0, and I'll write that down here, 0 to 1 minus r. I think I'm going to end off with theta because that's the usual order, even though it doesn't matter because that's constant and r is also constant. It's 0 to 1. So z is going to go from 0 to 1 minus r. I have a constant density function, but remember I still have to add in that z value. So I'm going to do dz r dr d theta. And then integrating with respect to z gives me a z squared over 2, 0 to 1, r dr d theta. Oops, sorry, 1 minus r. So that's going to be 1 minus r squared. Maybe I'll bring the 1/2 out in the front. It's going to irritate me. I don't like fractions. So this becomes 1 minus r squared. R dr d theta. Let's go ahead and 1 minus 2r plus r squared. Distribute the r on the outside. Okay, so this is r minus 2r squared plus r to the third dr d theta. And then integrating with respect to r, you have r squared over 2 minus 2 r to the third over 3 plus r to the 4 over 4. And I have 1/2, 0 to 2 pi. So 1 would be 1/2 minus 2/3 plus 1/4. I'm just going to write that as 1/12, I believe. Again, you guys double check me on this. D theta. 1/2 minus 2/3 plus 1/4. Seems okay. That's going to be 1 over 24 theta, which turns out to be the 2 pi over 24, which would be pi over 12. So remember, this is just the total moments. I still have to divide this for z bar by my mass, which was pi over 3. And that gives me a z bar of 1/4. Okay, so it was constant density, it was cone shape. It makes sense that the z value would be closer to the z is equal to 0 and further away from z is equal to 1, because it has to be closer to the larger or heavier side. So 0, 0, 1/4 makes sense to me when I found my center of mass. So this last example, we're going to find the center of mass of a region bounded by the upper half of a sphere, and the sphere is defined as rho equal to 6, which tells me it's probably going to be in spherical coordinates. It's bounded below by z is equal to 0, so the xy plane. We have a density function written with respect to rho, phi, and theta, which definitely tells me that I'm in spherical coordinates. And then my density function is 1 plus rho over 4. I want to sketch the region, and maybe I could use symmetry. Although my density function is not constant, notice that the density function does not have an x or a y value in it. It just has a rho value. Remember, rho is the distance from the center out. So what this tells me is that as my rho value gets larger and larger, that I have this uniform density changing from the center outward. So this might be a little hard to see. Well, let's sketch this first and talk about this. This is going to be the upper half of a sphere. So we have this upper half of a sphere. It's from the xy plane up. And imagine the rho value, so that would be the center outward. So as we go from the center outward, the density changes. But it's still this uniform change. So oddly enough, I can still use symmetry with respect to my x bar and my y bar. Because this object is actually kind of rotating about the z-axis. I could still use x bar and y bar as being 0. So it's going to be at the point 0, 0, but then it's going to go up from there. Maybe I could try a different color. So imagine being x, y, 0, and then we go up from there to find our center of mass. So I'm using symmetry here, and then I want to compute the mass. Unfortunately, because the density function changes, I can't just use the volume of half a sphere. I actually have to compute my mass. So recall that if I were to look at the shadow of this object in the xy plane, we simply have a circle of radius 6. And since I'm in spherical coordinates, I can see that my theta values are going to go from 0 to 2 pi. Phi we have to be careful with because it's just the upper half of the sphere. Imagine taking our phi is the angle from the z-axis, the positive z-axis out, right, or down. So if we go down, we'll end up at phi equal to pi over 2. So 0 to pi over 2 for our phi values, and then rho is going to be from 0 to 6. Just keep in mind that our center of mass is an x, a y, and a z. But now I'm at theta, phi, and rho. I don't see any x, y, z variables there. But I know from symmetry my x bar, y bar is 0, so I have to find my z bar. So we just have to be careful that when we compute z bar, we remember to put z into our integrand and then translate that to polar coordinates. So first of all, let's find our mass. I'm going to do theta on the outside, the usual order. So 0 to 2 pi, then phi is going to go 0 to pi over 2. And then from 0 to 6 would be my rho function. So my density function is 1 plus rho over 4. But then this is spherical, so I have the rho squared sine phi d rho d phi d theta. Alrighty, so computing, I would have to distribute the rho squared to get rho squared plus rho to the third over 4. And then I'm going to be, sorry, I didn't integrate it yet. Very impatient. And then I'm going to multiply that by the sine of phi. I can pull that out anyway since I'm integrating with respect to rho first. Okay, so that's going to be rho to the third plus rho to the fourth over 4 times 4, so 16. From 0 to 6. And I'll ignore the sine phi for now. Ooh, terrible handwriting. Let's see. So 0 is gone, but 6. If I plug that in my calculator, I think I get 153. So double check me on that, you guys. And then that's sine phi. D phi d theta. That would be negative 153 cosine phi. No, I could have pulled the negative 153 out. But I noticed that cosine of pi over 2 is 0, so it's going to be a minus negative, and the negatives would go away. So that's just going to be 153, and this is with respect to theta, so 153, 0 to 2 pi, theta. Sorry, I'm in kind of a little bit of a rush here. I thought I could beat the roosters, but they're coming out. Okay, so what is that? 306. Remember, this is just the mass. Now when we find our z bar, we have to be careful because the integral says to add z to our density function. Our limits of integration are going to be the same, and I'll probably run out of room, so skip some steps when it comes to the computation. So all these limits of integration are going to be the same, but remember we're going to take our density function and then times it by z. But I'm in spherical, so I'm going to have to change that z value to the spherical z value, which is rho cosine phi. Okay? And then I still have the rho squared sine phi d rho d phi d theta. Okay, I'm going to go ahead and distribute the rho times rho squared, so rho cubed. This is going to be rho cubed plus rho to the 4th over 4. And then on the outside I have cosine and sine of phi. Okay, so the integral with respect to rho would be rho to the 4th over 4 plus rho to the 5th over 20. And I'll just plug that value into a calculator. When I get a decimal. I think I'll just leave it like that, 712.8. So I'll go ahead and I'll leave it inside the integrand. I could pull it out, but I'll just leave it in there. That's 712.8. And then I have cosine sine of phi. What I'm going to do is something weird. I could do a substitution, but I'm too lazy to do that. Remember that 2 sine cosine is a trig identity. So if I were to write 712.8 as 356.4 times 2, I could replace the 2 cosine sine with sine of 2 phi, which is what I'm going to do. So this becomes 356.4 sine 2 phi. All right. And now when I find the antiderivative with respect to phi, sine of 2 phi is going to be negative cosine 2 phi over 2, which means this becomes, as I squish this in here, negative 178.2 cosine of 2 phi. All right. So cosine of 2 times pi over 2, so that's pi, will make this a positive 178.2. And then minus a negative 178.2. We'll turn this into 356.4 with respect to theta would just be 356.4 times 2 pi. And I'm going to skip all that stuff and just write 712.8 pi, which is fine. But remember, that was going back, that's actually not z bar. That's just finding the total moments, right? So to find the z bar, I have to take that value and divide it by the 306 pi. So let's go off to the side here. Z bar is equal to 712.8 pi divided by 306 pi. I'll put that in a calculator. The pi's cancel. I'll end up with 198 over 85 if I reduce things nicely. I think. Again, double check me, you guys. Yeah. So it's an ordered triplet, 00198 over 85. So kind of long, kind of tedious, but still doable. So that's it for this section.